Okay, first, good morning, good afternoon, and good evening, everyone. Thank you and welcome again to the Forum of Young Researchers on Detonation. And this is our last episode, the finale of season 2. And I would like to thank you all for attending for most of the episode of the season and also your participation. And we will soon start making plans for the next episode, next season, which will likely start in late summer and run through the fall. And if you volunteer, you want to present your interesting work on detonation, or you have suggestions or recommendations for a good candidate as our speakers, please let us know, and you're all welcome. Right. And today our speaker is Dr. Hiroaki Watanabe, and I will give like a short introduction of him. He received his PhD degree in engineering at the Keio University, Japan in March 2020, under the supervision of Professor Akiko Matsuo for the numerical analysis on the dynamics of a gaseous detonation with dilute water spray. During the PhD course, he stayed at the École nationale supérieure de mécanique et d'aérotechnique, Institut Pripret, in France for 5 months and worked with Professor Ashwin Chinaya, who accepted guest professor in Keio University and was his second advisor in the PhD course. From April 2020, he is an assistant professor at the Department of Aerospace Engineering in Nagoya University, Japan, and works with the Professor Jiro Kasahara, Professor Ken Matsuoka, and Professor Akira Kawasaki, and Professor Noboru Ituyama. His research interests include the physics of two-phase detonation and the detonation combustor. And we would like ask the attendees to please write your comment or questions in chat during Hiroaki's talk, and we will discuss with the speaker by the end. And also we will be recording the video, and upon the speaker's approval, we will upload the video to YouTube and the Bilibili. And next, I will give the podium to Professor Watanabe. Please go ahead here.
Okay, thank you very much for Xiaoxian for the introductions. And I am Hiroaki Watanabe from in Nagoya University, and now working as an assistant professor in the Nagoya University. This work is part of my PhD research in the Keio University, and this is a collaborative research with Keio University and ASMA and Nagoya University. And firstly, I would like to, I will introduce the research motivation of my research. The main motivation for the detonation research comes from the following 2 points: engineering application for the detonation combustor and the safety engineering for the mitigation of the detonations. So a lot of study of the detonation phenomena is conducted in the past, and a lot of knowledge are obtained. However, there are still issues for the practical practical use of the detonation combustor and the safety measurement. For the practical use of the detonation combustors, the use of the liquid fuel is very attractive because of the high energy density content. Also, one of the potential solutions to mitigate the damage is the use of the water spray to mitigate the detonations. So the knowledge on the two-phase detonation is required and get attention. So in my study, the gaseous detonation with direct water spray is focused on. Basic research is conducted on the gaseous detonation propagating through the mixture with water droplet. One of the experimental study is conducted by Josler et al. They use the ethylene and air mixture and the water droplet as sprayed. The cell structure in the experiment are shown in this slide. The left figure is a case without water droplet, and the right figure is a case with water droplet. From the comparison between these two figures, the cell width increase by addition of the water droplet, and velocity decrease up to 5% is confirmed in the experiment. From the previous research, the characteristic of gaseous detonation with direct water spray is clarified. However, the structure of gaseous detonation with direct water spray and the droplet behavior inside the detonation wave remain partially understood yet. Therefore, I tried to elucidate phenomena during my PhD studies. So several studies on the gaseous detonation with direct water spray were performed in the past from the point of the safety engineering. Therefore, the main concern was to clarify the condition for water spray to quench the detonation effectively. In this slide, we briefly review the previous studies on the droplet condition required for the mitigation of the detonations. Thomas et al. Studied the quenching of the detonation by water spray and observed that the fine spray quenched the detonations. On the other hand, Numerical et al. Studied the quenching of the detonation by water spray and indicate the possibility of the coarse water spray for the detonation quenchings. The discussion on the effect of droplet size and condition is very active, and the general guideline for the droplet size is not achieved due to the different conclusion on the droplet size. Therefore, the behavior of the water droplet is needed to be clarified in order to understand the phenomena and obtain the general guidelines. The droplet breakup behavior with a vertical shock wave are active here, and the knowledge on the droplet breakup are developing. On the other hand, the gaseous detonation has a stellar instability, and its front shape is completely different from the vertical shock wave as in the schematic figures. To clarify the droplet breakup behavior in the detonations, we need to answer these questions. Where and how do droplet break up behind the detonations? To the best of my knowledge, the following are still unknown in the previous studies. So firstly, the droplet breakup behavior during the propagation of the gaseous detonation with direct water spray. And secondly, the droplet life inside the cellular structure of gaseous detonations. This knowledge will be useful for the establishing guideline on the conditions for the water droplet to mitigate the detonation effectively. In addition to the droplet behavior, the knowledge of the structure of the detonation with direct water spray is also needed to improve our understanding of the phenomena. Up to now, the structure of gaseous detonation with direct water spray is not fully understood yet. The schematic of the main structure of gaseous detonation is shown in this slide. From the previous study, the detonation wave has at least 3 characteristic lengths: induction length and reaction length, and the hydrodynamic thickness, which is the distance from the shock wave to the mean sonic plane. For the droplet, the following 4 characteristic lengths exist: temperature equilibrium, velocity equilibrium, and breakup and evaporations. Here, we have the question for the mean structure of gaseous detonation with direct water spray. Where do these droplet events happen inside the gaseous detonations? The detonation structure with water spray will provide us the basis of the propagation mechanism, and I will answer for the question for the one of the specified case. To achieve this goal, the 2-dimensional numerical simulation are used to obtain the detailed information on the flow field, and the analysis is performed to answer the question for the gaseous detonation with direct water spray in a 2-dimensional straight channel in this study. This presentation can be divided into the 2 parts. In the first part, the main structure of gaseous detonation with direct water spray is focused on to clarify the main structure and interaction between the 2 phases. In the second part, the droplet behavior during the propagation of the gaseous detonation is analyzed to specify how the water droplet break up and behave inside the cellular structures. The reference for the today's presentation are following 2 papers and my PhD thesis. The first one is my paper in the Journal of Fluid Mechanics, and the result in the part 1 is based on these papers. And the second one is my paper in the recent proceedings of the Combustion Institute. The result is summarized in the part 2 from this paper. And my PhD thesis contains the result in these 2 papers. And the major part of my chapter 5 in my PhD thesis is based on the JFM paper. However, there is additional figure and discussion because I wrote it after the acceptance of the papers. And the sum of the chapter 6 is summarized in the reference 2, and you can find the additional results from the droplet breakup and the behavior in the chapter 6 in my PhD thesis. Next, I will explain the mathematical modeling using the present study. The precondition for the droplet present simulation is briefly reviewed in this slide. And the schematic figure are shown here. For the gaseous detonation with direct water spray, the order of the volume fraction is 10 power minus 6 to 10 power minus 5 and very dilute. In addition, the droplet diameter is order of 10 micrometer and very small. Furthermore, the droplet breakup is taken into account, which means that the polydispersed spray will be generated, and Eulerian method is difficult to track the droplet history for the droplet breakup. Therefore, the Eulerian-Lagrangian method is appropriate to model the gaseous detonation with direct water spray, as shown in the schematic figure. In the Eulerian-Lagrangian method for the gaseous phase, the gaseous phase is solved based on the computational cell as in the Eulerian method, as in the schematic figures. To treat the multi-phase future in the gaseous phase, the two-phase model is used. For the modeling of the droplet, the Lagrangian method is applied to track the droplet motion accurately. The droplet is solved as discrete particle, as in the schematic figures. The governing equation needs to take into account the region where the gaseous phase does not exist due to the droplet volumes. The porosity, namely the gas volume fraction, is introduced, and the schematic figure are shown in this slide. The porosity in the two-dimensional case is calculated from these equations. The droplet is modeled by the Lagrangian method and exists independently on the computational cell. So the porosity is calculated using the ratio of the total volume, which rotates inside the computational cell, to the computational cell volume. For the summation of the total volume, which rotates inside the computational cell, the particle centroid method is utilized. And this slide shows the governing equation for the gaseous phase. The governing equation for the gaseous phase are volume average to the compressible Navier-Stokes equation with a source term for the chemical reaction, interaction with droplet, and nozzling term to treat the multiple futures. The equation states for the ideal gas is used to close the system. For the chemical reaction for the hydrogen-oxygen mixture, the detailed chemical reaction model proposed by Hong et al., which considers 9 species and 20 elemental reactions, is utilized. The governing equation for the droplet are shown in this slide. The governing equation, the Lagrangian method is used to model the droplet to track the droplet motion accurately. So the governing equation are Newton equation motion and energy conservation equation, and droplet mass equation and droplet number density equations. Evaporation and droplet breakup is taken into account as the droplet modeling. The droplet evaporation is estimated by the model by the Abramazon et al. This model is based on T2 evaporation law, and the mass and heat transfer by the evaporation are expressed in these equations, and droplet radius decrease by the evaporations during the simulations. For the force acting on the droplet, the quasi-steady force and the pressure force are taken into account. The equation to estimate the force are shown in this slide. The quasi-steady drag force is a function of the relative velocity and particle radon number and particle Mach number and the gas volume fractions. The convective heat transfer is considered as the energy transfer by the temperature differences. The Biot number is much less than 1 in these simulations. So the temperature gradient inside the droplet can be neglected, and the surface temperature is equal to the droplet temperature. Convective heat transfer is calculated from these equations. To calculate convective heat transfer, the local heat transfer coefficient is estimated from the empirical equation of Rand-Marshall equations. The droplet breakup is taken into account in these simulations. The criterion for the droplet breakup is shown in this slide. The governing parameter for the breakup is Weber number, and its definition is shown here. The Weber number represents the ratio of the inertial force acting on the droplet to the surface tension force. The droplet breakup occurs if the Weber number exceeds the critical Weber number. The critical Weber number is estimated by Brodocki et al. In this formula. The critical Weber number is function of ornithology number is around 12 in the present simulation conditions. The droplet breakup is modeled based on the model by Chauvin et al. The procedure for the calculation for the droplet breakup in this model is explained from 3 slides. The schematic figure for the droplet diameter evolution during the breakup process are shown in this slide. The droplet breakup occurs under the assumption that the droplet diameter change linearly during the breakup process. That is, the droplet diameter change from the initial state to the maximum stable diameter during the total breakup time, as in the schematic figure and the equations. The droplet breakup is modeled by the number density, and the source term for the number density appear when the droplet breakup. From the assumption of the linear change from the droplet diameter, the production rate for the number density can be written as following equations. The parameter for the calculation for the production rate for the number density is maximum stable diameter and total breakup time, shown in the left square in these equations. For the estimation of the maximum stable diameter, the stability criterion is used to deduce this value at these equations. And the total breakup time is calculated from non-dimensional total breakup time from these equations. The non-dimensional total breakup time is estimated from empirical correlation by Pirch and Edelman in this study. The validity of the present breakup model is confirmed through the comparison of the present experimental result on the interaction between the shock and the cloud of water droplet. The numerical methods are listed in this slide. For the discretization of the convective terms, the fifth order awesome PW plus by modifying one of that is utilized. And the other numerical methods are shown here. The recycling block method is utilized to reduce the computation cost in this study, and the schematic figure are shown here. A small computational domain, which encompasses the main radiation shock waves and main sonic plane for the detonation front propagation, are shown in this schematic figure. This procedure enables the detonation to propagate a longer distance enough to obtain the main quantities. Now, I move to the result and discussion. The part 1 presents a quantitative analysis on the mean structure using the weakly and stable mixtures. The mean structure is estimated by Favre-averaged one-dimensional profile for both gaseous phase and water droplet through the comparison of the characteristic lengths. The characteristic length for the gaseous detonations, the induction length and the reaction length and the hydrodynamic thickness are important length scale. For the droplet, following 4 characteristic length scale can be considered: temperature equilibrium, velocity equilibrium, and breakups, evaporations. The aim of this chapter is to understand to which extent the 3 detonation characteristic lengths and 4 droplet characteristic lengths can be intertwined and how these processes interact with each other. The schematic of the computational target is shown in this slide. The mixture used is 40% nitrogen dilute with a stoichiometric hydrogen-oxygen mixture with an initial pressure of 10 kilopascal and a weakly unstable mixture to make it easier to analyze the mean structures. The 2D developed gaseous detonation propagates through the unbalanced mixture with a water droplet in a straight channel. The channel width is 39 millimeters and 1/2 cell exists inside the channel. The initial droplet diameter is 50.99 micrometer and liquid apparent density is 5.5 grams per cubic meters. The minimum grid width is 50 micrometers and the resolution is about 34 points in a half reaction length. In addition, the grid width is 3 times larger than the droplet size, and the resolution is enough to reproduce the droplet motions in these studies. The length of the detonation propagation after the first contact with water droplet is 900 millimeters and the order of 1 meter by applying recycling block method. In addition, the backward boundary is transmissive boundary, which means that the effective reflection wave does not exist in these present simulation conditions. The flow field for the gaseous detonation with direct water spray is shown in this slide. Upper figure shows the temperature flow field, and the lower figure shows the droplet diameter in the discrete Lagrangian plot. So the white color in the lower figure means that there is no droplet. Gaseous detonation propagates from left to right. So please watch the movies. So the detonation wave keeps propagating through the mixture with direct water droplet. And the droplet diameter rapidly decreases by the droplet breakup, and evaporation makes the droplet diameter small as time passes. As a result of the interaction, the average propagation velocity is 3.8% lower than the Chilean velocity. From this numerical result, I applied the statistical Favre-averaged techniques for both gaseous phase and droplet and obtained the characteristic length. This slide shows the Favre-averaged Mach number profile to estimate the hydrodynamic thickness. The horizontal axis of this figure is normal distance from the shock waves, and the vertical axis is the Mach number in the main shock frame. The red line is the case with water droplet, and the black line is case without water droplet. The gas sound speed is used to define Mach number. For the case with water droplet, the Mach number based on the gas sound speed decreases due to the decrease in the gas velocity and endothermic evaporation by the water droplet. As a result, the hydrodynamic thickness is increased. This slide shows the Favre-averaged summitity to calculate the characteristic length for the chemical reactions. The red line is the case with water droplet, and the black line is the case without water droplet. The enlarged view of the figure for the gray region is shown in the right side. The summitity does not change much by the addition of the water droplet in the wall regions. By the close inspection near the shock front in the enlarged views, the maximum summitity position increased by the water droplet. From this summitity profile, the induction length is about 2 times, and the reaction length is almost the same. This slide shows the Favre-averaged Weber number profile and to characterize the droplet breakup, and the number density profile, which signifies the degree of droplet breakup. The droplet breakup occurs when the Weber number exceeds this critical Weber number showing the dot black line in the upper figures. Weber number become maximum behind the shock and then fall below the critical Weber number, which comes from the decrease of droplet diameter toward its equilibrium value, but also due to the decrease of the relative velocities. As a result of the breakup, one single parent droplet fragment into 60 the droplet in the row physics. In this study, the characteristic length for the end of breakup is defined at the distance from the shock wave to the position where the Weber number below the critical Weber numbers. Under the present simulation conditions, the characteristic length for the end of breakup is estimated to be 4.9 half reaction lengths, and the breakup complete after the induction zone. In order to quantify the influence of additional water vapor from the evaporation on the reactivity of the gaseous mixtures, the Arrhenius plot for the hydrogen is shown in this slide. The horizontal axis is the inverse of the temperatures, and the temperature is lower in the right side. From the comparison of the characteristic lengths for the induction zone and breakup in the previous slide, the breakup complete downstream of the induction zone in the present conditions. The chemical reaction starts from the lower temperature, thus with a water droplet due to the decrease of the propagation velocity. However, the slope is almost the same regardless of the presence of the water droplet, which means that the global activation energy in the induction zone and the reaction zone does not change by the evaporation of the water droplet. This slide shows the Favre-averaged scale of droplet diameter profile to estimate the end of evaporations. From the previous slide, the droplet breakup occurs in a narrow region behind the front, and droplet diameter rapidly decreases by the breakup in these gray regions. After the breakup finished, the droplet diameter decreases only by the evaporation, and square of droplet diameter can be seen to vary linearly with the distance from the shock, which is reminiscent of the evaporation due to rho. Therefore, the characteristic length for the end of evaporation is defined at the distance for the shock wave, distance for the water droplet to be completely evaporated, and is evaluated from a linear approximation after the breakup, showing the black lines. The characteristic length for the end of evaporation is estimated to be 153.8 half reaction lengths. The Favre-averaged gas and water droplet temperature are shown in this slide to calculate the characteristic lengths for the temperature saturations. The red line is the gaseous temperature, and the blue line is droplet temperatures. The gas temperature increased by exosomes chemical reactions. The water droplet temperature also increased due to the convective heat transfer with the gas phase, and then reached the saturation temperature at the distance of 2.9 half reaction lengths, of which will be shown to be the fastness of all the reactivation processes. The temperature of the water droplet does not equivalent the gas temperature, which means that the temperature equilibrium is not achieved. The characteristic length for the temperature saturation is defined as the distance from the shock waves to the position where the water droplet reaches the saturation temperature, and is estimated at 2.9 half reaction lengths. This slide shows the Favre-averaged gas and droplet X velocity in the laboratory frame to estimate the velocity equilibrium. The red line is the gas velocity, and the blue line is droplet velocity, and black line is relative velocities. The gas velocity in the laboratory frame gets accelerated by the shock waves and then decreases due to the expansion of the band gases. The water droplets are accelerated due to the quasi-steady drag force and the pressure force. Due to this momentum transfer, the velocity of the gas, the velocity of the droplets increase, and that of the gas decrease to the equilibrium values. As a result, the relative velocity in the x direction is maximum immediately after the shocks, and then gradually decrease to 1/10 of the maximum at the distance of 17.5 reaction lengths from the mean shock wave positions. The characteristic length for the velocity equilibrium in the x direction is defined as the distance from the shock waves to the position where the relative velocity decreases to 1% of its maximum. The characteristic length for the velocity equilibrium is deduced from the slope of the relative velocity in a log scale is estimated to be 304.6 half reaction lengths under the present simulation conditions. The schematic of the main structure of gaseous detonation without water droplet in the present analysis is shown in this slide. The horizontal axis is distance from the shock waves by the half reaction length and written in a log scale. As in the previous studies, the gaseous detonation consists of the beginning shock waves, induction zone, and reaction zone, and the sonic plane in this sequence. Then, I will plot the characteristic length for the gaseous detonation with dilute water spray based on the previous analysis in the lower side. The upper side is the mean structure without water droplet, and the lower side is mean structure with water droplet. The red line denotes the characteristic length for the gaseous phase, and the characteristic length relating the droplet are shown in the blue lines. The gaseous detonation with dilute water droplet consists of the raging shock waves, induction zone, and reaction zone, and the mean sonic plane as those of the gaseous detonation with water droplet. However, the induction length and reaction length and the mean sonic plane are increased due to the interface interaction with the water droplet and the lower propagation velocities. For the present simulation condition, the process for the droplet to reach the saturation temperature is the fastness interface interaction, and it occurs after the induction length. After that, the breakup which occur and end at 5 half reaction lengths will produce a smaller droplet, enhancing the overall interface exchanges. However, the breakup is performed after the induction zone. Thus, the additional water vapor from the evaporation does not influence the main reaction zones. The evaporation proceeds well after the sonic planes, and the velocity equilibrium is also achieved in the end. These characteristic lengths are intimately intertwined and characterize the main structure of steady gaseous detonation with dilute water droplet. The main conclusion in the part 1 are summarized in this slide. The main structure of gaseous detonation with dilute water spray for weakly unstable mixture is investigated by two-dimensional numerical simulations, and the following knowledge is obtained. The characteristic lengths of the gaseous detonation and interface exchange have been quantitatively ordered under the present simulation condition for the first time. The main structure of gaseous detonation with water droplet shares similar structure without water droplet. The droplet breakup finish after the induction zone in the present simulation conditions, and the additional water vapor from the evaporation doesn't affect the reactivity of the gaseous mixtures. Next, the part 2 presents a qualitative analysis of droplet behavior during the propagation of the gaseous detonation with dilute water spray using a weakly unstable mixtures. The droplet behavior is analyzed to quantify how the water droplet break up and behave inside the cell of the gaseous detonations. The schematic of the computational target is shown in this slide. The simulation condition is completely the same in the part 1. So the simulation condition is briefly reviewed here. The mixture used is 40% nitrogen diluted stoichiometric hydrogen and oxygen mixture with the initial pressure of 10 kPa and weakly unstable mixtures. The 2D developed gaseous detonation propagates through the ambient gas mixture with water droplet in a straight channel. The droplet diameter is uniform at 50.9 micrometer, and liquid apparent density is 5.5 gram per cubic meters. The Weber number, which characterizes the droplet breakup, and the number density for the instantaneous flow field are shown in this slide. The Schmidt image is also superimposed in the figures. For the Weber number distributions, the Weber number began maximum behind the shock waves and then decrease, which come from the decrease of droplet diameter toward its equilibrium value, but also due to the decrease of the relative velocities. The droplet breakup occurs when the Weber number exceeds the critical Weber numbers. The lower figure shows the droplet number density, which signifies the degree of droplet breakup. For example, the value of number density is equal to 100. One parent droplet fragment is to 100 delta droplet. Although the droplets are uniformly distributed in the initial conditions, the degree of the droplet breakup process spatially varies behind the front, as shown in the number density distributions. Firstly, the process for the droplet breakup is visualized in this slide. Left figure shows the number density distribution, and the right figure shows the movie for the production rate for the number density, which means that where the droplet breakup occurs. The gray color in the right figure means that droplet does not break up at this time. The Eulerian image is superimposed in this figure. So please watch the movies. For the movies, the droplet breakup occur preferentially behind the front, as shown in the number density distributions. Preference and production rate for the number density. As a result, the degree of breakup change spatially from the number density distributions. From the next slide, the cause of inhomogeneous droplet breakup process will be analyzed using the instantaneous flow field. The four factors for the droplet breakup during the propagation of the gaseous detonation exist, and they will be focused on the following two slides. The enlarged view near the detonation front is shown in this slide. Left figure is the droplet accelerations, and the right figure is the production rate for the number density. The gray color in the right figure means that the droplet does not break up at this instantaneous time. The Eulerian image is superimposed in both figures. The droplet motion characterized by the droplet acceleration is induced by the following four factors. The jet emanating from the collision continuously accelerate the water droplet toward the propagation direction as in the white dot cycle. Also, the transverse wave collision locally forces the water droplet to accelerate. The strong droplet acceleration correlates with the high relative velocity and strong inertial force compared to the surface tension acts on the droplet. As a result, the droplet breakup occurs as in the figure of the production rate for the number density, and the droplet breakup occurs by the jet and the transverse wave collision behind the front. The instantaneous flow field after the 5 microseconds from the previous slide is shown in this slide. After the local explosion, the storm mass system forms and the transverse wave propagates perpendicular to the propagation direction in the middle of the channel. The water droplets are accelerated by the transverse wave after the local explosion in the white dot cycle. Then focus on the region near the bottom wall. The transverse wave move upward and interact with the receding jet at the white dot cycle. The interaction causes the acceleration of the water droplet toward the propagation directions. The droplet breakup also occurs by these transverse waves and the interaction between the jet and transverse waves for the production rate for the number density. The process for the droplet breakup mentioned above repeats during the propagation of the gaseous detonations. The number density at the same instantaneous time is shown in this slide. Consequently, this event for the droplet breakup happens behind the front inhomogeneously, and the degree of droplet breakup spatially changes behind the front, as shown in the number density distribution in these figures. Let me summarize the main findings for the mechanism for the inhomogeneous droplet breakup process during the propagation of the gaseous detonation with dilute water sprays. The schematic for the droplet breakup in the detonation is shown in this slide. From the instantaneous profile analysis, the droplet breakup during the propagation of the gaseous detonation with dilute water spray occur primarily by the following factors: the jet and the transverse waves, and interaction between the jet and transverse waves. These processes are shown in the red square in the schematic figures. The droplet breakup occurs inhomogeneously during the propagation of the gaseous detonation by these reasons. In order to determine the outcome of the parent droplet, the scatter plot for the non-dimensional total breakup time, normalized by the initial characteristic time, is shown in the left side. and the dynamic pressure distribution is shown in the right side. The color in the scatter plot represents the droplet diameter at the end of the breakup. As it can be expected from the curvature and unsteadiness of the leading shock waves, the computations show the broad spectrum of non-dimensional total breakup time, which is unique in the shock-induced flow in the black lines. The non-dimensional total breakup time become longer than that estimated for the post-shock conditions due to the change in the dynamic pressure behind the front. This trend is in line with previous experimental results on the spread detonation by Droplet et al. In addition, the final droplet diameter can also be polydispersed, even if the initial diameter is monodispersed. From the previous slide, the polydispersity in the droplet diameter for monodispersed spray arises during the propagation of the gaseous detonation with dilute water sprays. So the origin of the polydispersity in the droplet diameter is analyzed in the following slide. The droplet diameter at the end of the breakup in the initial position is shown in the upper side, and the maximum pressure history is shown in the lower side. The region with small droplet diameter at the end of breakup does not correspond to the high propagation velocity due to the induced droplet movement and after the passage of the front and the presence of the jet. In order to obtain the insight into the origin of the polydispersity in the droplet diameter, the behavior of the water droplet is qualitatively analyzed by categorizing the water droplet based on the breakup intensities. The water droplet is divided into the three groups based on the breakup intensity. The criteria for the high breakup intensity group is that the droplet diameter at the end of the breakup is below 4 micrometers, and the water droplets are categorized as low breakup intensity groups when the droplet diameter at the end of the breakup between 5 and 6 micrometers in the present studies. And the other droplets are categorized as other breakup intensity. And high breakup intensity in the red color and the low breakup intensity in the blue color in the lower figure will be focused on to see the difference and the origin of the polydispersities. The Favre-averaged one-dimensional profile for the droplet diameter and Weber number based on the breakup intensity is shown in this slide. The mean equilibrium diameter in the left figure changed by the level of breakup intensities. The Weber number falls below the critical Weber number around 5 half reaction lengths from the shock front, and the profile for the Weber number does not change much by the level of breakup intensity as shown here. And the breakup process and the droplet diameter distribution for the water droplet with high and low breakup intensity are analyzed through the probability density function for the droplet diameter as a function of the distance from the shock to the water droplet positions. The top figure is a PDF at 0.5 half reaction lengths from the front, that is, just behind the front. And the middle figure is PDF at 3 half reaction lengths from the front, middle of breakup process. And the bottom figure is PDF at 5 half reaction lengths from the front at the mean end of the breakup process. At the initial stage of the breakup process, the distribution of the droplet diameter is similar between the high and low breakup intensity cases. In the middle of breakup process, the distribution of the droplet diameter starts to change, and the two peaks are observed in high breakup intensity cases, which means that the droplet breakup is induced by the transverse waves and jet after the passage of the front. And the distribution at the mean end of breakup process in the bottom figure are totally different from each other. The origin of the polydispersity is linked with instantaneous flow field in this slide. Left figure shows the instantaneous flow field of the final droplet diameter at the end of the breakup at the actual position with the Eulerian image. Also, the schematic for the breakup process in the detonation is shown in the right side. For the left figure, The droplet with small final droplet diameter at the end of the breakup experience one of the events in the schematic figure, and the breakup occur more intensively than the other droplet. Here, I've shown jet and transverse wave and the interaction between the jet and transverse wave. So the polydispersity for the spray mainly come from the local phenomena downstream of the shock, such as the jet and the transverse wave, and interaction between the jet and transverse waves, and the combination of both. The summary in the part 2 is shown in this slide. The droplet behavior during the propagation of the gaseous detonation with dilute water spray for weakly unstable mixture is investigated by two-dimensional numerical simulation, and the following knowledge is obtained. The droplet breakup during the propagation of the gaseous detonation occur inhomogeneously behind the front by the jet and transverse waves, and the combination of both. The polydispersity in the droplet diameter for monodispersed spray emerge by the event after the passage of the front, namely the jet and transverse waves. And the non-dimensional total breakup time become longer than that estimated from post-shock conditions, and this trend is in line with previous experimental result on the spray detonations. And finally, main conclusion shown in this slide. In the part 1, for the quantitative analysis on the mean structure, the characteristic lengths on the gaseous detonation and interface exchange have been quantitatively ordered under present simulation condition for the first time. The mean structure of gaseous detonation with dilute water spray shares a similar structure with a water droplet. In the part 2, the qualitative analysis of droplet behavior during the propagation of gaseous detonation with dilute water spray, and the position where the droplet breakup occur in the detonation is specified, and the jet and transverse waves have a dominant role in inducing the droplet breakup and the polydispersity from monodispersed spray. And this is all for my presentation, and thank you for your kind attention. And if you have any question, even after my presentation, please contact me for working email address. That's all.
Okay, thank you, Hiroaki. Very interesting talk. And we already have one question from Professor Huangwei Zhang in the chat. Could Professor Zhang ask directly?
Okay, thank you very much. Dr. Hiroaki, thank you very much for a very nice talk. I have a very small question about number density. Maybe I missed something. So is it actually a Eulerian quantity instead of a Lagrangian quantity? Because here from your slide, it is solved from the ODE, right? From a system to model the breakup process. So actually, number density is also visualized from the Lagrangian droplets, right? Can you clarify this?
Explain.
Yeah, thank you.
So firstly, I will show the governing equation first. Wait. And this is the governing equation for the Lagrangian for the droplet modeling. In my model, I solve the number density to model the droplet breakup, and number density is a Lagrangian quantity in my model. And the breakup is modeled by this Chauvin model.
So because the Lagrangian governing equation are for droplets, right? So if you solve it for the droplets, that means actually this number density is for droplet instead of for the CFD mesh, right?
Yes, of course. Number density is
so
for the Lagrangian.
Okay, so actually in your simulation, droplets each droplets are checked, or it's somehow like using a virtual droplet or computational droplet, or some.
That's right.
Okay, so initially, actually, for each droplet, how many real droplets you have?
How many?
Yeah.
Yes. In this simulation, I use a parcel samples as you use, and one parcel represents about 6 droplets in this case.
Okay. 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 I understand. Okay.
And I also check the resolution study for the number of parcels, and this is the resolution for the path is enough for my case.
Okay. Okay. Thank you.
Wait.
Okay.
Okay.
Yeah, thank you for the question. Any other questions or comments from the audience?
Xiaochen, maybe ask another one.
Sure. Yeah, go
Okay,
ahead,
of course, please.
Yeah. So also for this slides, no, I think the governing equation for the Lagrange, here. So because here you consider the jag and also the pressure gradient, right? So did you actually compare the magnitude of these two terms? Are they important actually? Particularly the second one. The first one, of course, is important. How about the second one, the pressure gradient?
As you said, the first one, the quasi-steady force is dominant for the compared to the pressure gradient field. I will show the graph. Wait, I have a lot of supplementary material and I have to find it.
Okay, no problem.
Wait for five.
Okay.
I have one slide. And wait. Yes, I have one. Yes, can you see? This is the Favre-averaged
yes.
force on the rigid phase. And the solid line is the x direction, and broken line is the y direction, and red line is quite steady drag force. So the order of these is three order, or four, yes, 1, 2, 3. Order.
So actually, two to three order magnitude lower, right, for the pressure force. Yeah, even near the leading shock wave, right?
Yes, that's right.
Yeah. Okay. Thank you very much. Thank you. So this is all my
question.
Yeah. Thank you. Yeah. Thank you for your presentation.
Any other questions? Actually, I have two questions. The first one is on slide number 34. You show this different length scales behind the shock, like yeah. I see like this sonic plane is it's about like 3 times longer than where the reaction zone ends. I just wonder, like, well, according to this generalized CJ theory, that means like if you have the rate of heat release stopped, that has to be where the sonic plane is, right? So if you have your reaction on average ended at around like 13 times the half reaction zone length, then for the rest, there is evaporation of the droplet, which is an endothermic reaction, endothermic process. So I just wonder, how can you, like, what's the physics keep accelerating the flow behind the shock towards sonic point?
Okay, I see. So I will show the master equation first to explain it. Wait. Yes, in my JFM paper, we discussed the master equation for the two-phase flow, and in this case, master equation have the summity have following four terms: heat release term and interface interaction, mass transfer and momentum transfer and energy transfer terms. So each term has different roles on the accelerating or decelerating the gaseous flow. And this is the total one. The blue one is sonic parameter, and red one is generalized global summity. So it means that general summity and general CJ condition is satisfied at this point. So, and I will have the each term distribution for it. I will show which term is dominant. So, let me see. I will have to find it.
No more.
Or if you have, maybe I will share my JFM paper first.
Okay.
I have figure in that slide.
Okay. Yeah. Yeah. That's fine.
Wait. Yes, different. Can you see this my papers?
Yeah, I can.
we discuss in the master equation in which, yes, this section. Yes. So we decompose the summity by the different effect and plot it in this figure 17. So the solid volt red one is total summity one. The blue one is mass transfer, which means the evaporations, which act on the accelerating the gas phase as shown here. And for the momentum transfer, which is a green one, it is first decrease the gas phase due to the momentum transfer, but after that, it turns to be the positive due to the evaporation of the water droplet. Evaporating water drop, the momentum of evaporating droplet transfer to the gas phase, so accelerate the water drop, accelerate the gas phase. For the energy transfer is blue one, yes, not yes, orange one. So it is all negative loss in the gas phase velocities due to the energy endothermic evaporations. So as a balance, this summity is balanced at this point and is almost correspond to the Mach number 1, and which means the generalized condition is achieved in this case.
Okay. Okay, I see. But I still have a further question. Is if you look at your overall total thermicity, it shows this non-monotonic behavior. So it actually goes down to negative in a large region. But how come in this negative thermicity or the endothermic region that the flow is still accelerating but not decelerating? Right. So you can see like that your like the Mach number of the flow is going down monotonically. That means it's accelerating with respect to the leading shock. But you actually go under this total endothermic region. Just this I don't know how to rationalize this.
Yes, me too. We have difficulty to understand this one. And
anyway, then this is not to be answered now, but I think this interesting phenomenon. Maybe we all need to think a bit more about this. And I have another a small technical question. I'm just curious, in your simulation, because you're doing 2D simulation, but the droplet, the Lagrangian model is actually for a spherical object, right? Like for 3D. Like how you actually consider the space in the Z direction, right? Because when you convert your Lagrangian source term to the gas phase, to the Eulerian mesh, you need to divide by a cell volume, like this S cell, I think you call it. Like how you compute this S cell? Is it just dx times dy or dx times dy times n number of dz? Like how you consider that?
So for the Z direction, I consider the unit length. You want to consider the volumes. And for the calculation for the droplet breakup in my model, the droplet breakup is model for the empirical correlation, so which considers three-dimensional effect. So even if the calculation is 2D, the breakup can be reproduced qualitatively.
Okay. So if your dz is just like unit length, or in this case, since you're using a metric system, then that means it's 1 meter, right? So there's maybe a suggestion I will give you guys is I think this will like the mass fraction or the volume fraction you characterized for the droplets is actually more dilute than what you want, right? Like because each grid is like a box, which is 50 micron times 50 micron and times 1 meter, right? Then you put like one single or a number of droplets there, right? So I think it's more diluted than what is actually is like with the assigned mass fraction or volume fraction of the droplets, right? Yeah, probably like if you consider that dz to be the average spacing between the particles initially, I think that's more reasonable. Then you have your initial droplet mass fraction the same as what you want as an input parameter, right? So yeah, that's just my suggestion.
Thank you.
Thank you. Any other questions from the audience?
Yes, I have a comment, Xiaocheng.
Yeah, sure, please go ahead.
So it's a comment in regards to Xiaocheng's comment question as to why is the sonic surface behind the end of the reaction zone, and the physical understanding of this is that there's a delayed energy release that happens from the transverse modes into the mean flow that happens behind the reaction zone. So in a cellular detonation, there's transverse oscillations that carry momentum and energy, and those are dumped back into the mean flow slower than the energy release. So that's why the energy, the sonic surface is delayed. We explained that in ages ago,
right,
in our work on this subject, maybe 15 years ago or so.
Yeah, that sounds sense. I agree.
Okay.
Thank you very much.
Yeah.
For the comment.
Thank you. That's clear. Yeah. Thank you. Any other further questions or comments? If there's not, then I would like to thank our speaker, Dr. Watanabe, again. Thank you for your time preparing the talk and your participation. And thanks to everyone who attended and presented in this forum for the whole season. Yeah, this is the end of this season 2, and we will start planning for season 3 soon. And season 3 will tentatively be scheduled in from late summer to maybe mid or late fall 2021. And if you want to present your own work or you have suggestions for us to look for like more speakers, please let us know. All the suggestions are welcome. And I would like to thank you all again, and have a good summer and have a good day. Yeah, thank you. Bye-bye.